In machine learning, naive Bayes classifiers are a family of simple probabilistic classifiers based on applying Bayes' theorem with strong independence assumptions between the features. Naive Bayes models are also known under a variety of names in the literature, including simple Bayes and independence Bayes. All these names reference the use of Bayes' theorem in the classifier's decision rule, but naive Bayes is not a Bayesian method. Russell and Norvig note that, naive Bayes is sometimes called a Bayesian classifier, a somewhat careless usage that has prompted true Bayesians to call it the idiot Bayes model. Naive Bayes has been studied extensively since the 1950s. It was introduced under a different name into the text retrieval community in the early 1960s, and remains a popular method for text categorization, the problem of judging documents as belonging to one category or the other with word frequencies as the features. With appropriate pre-processing, it is competitive in this domain with more advanced methods including support vector machines. It also finds application in automatic medical diagnosis. Naive Bayes classifiers are highly scalable, requiring a number of parameters linear in the number of variables in a learning problem. Maximum likelihood training can be done by evaluating a closed-form expression, which takes linear time, rather than by expensive iterative approximation as used for many other types of classifiers. Introduction. In simple terms, a naive Bayes classifier assumes that the value of a particular feature is unrelated to the presence or absence of any other feature, given the class variable. For example, a fruit may be considered to be an apple if it is red, round, and about 3 inches in diameter. A naive Bayes classifier considers each of these features to contribute independently to the probability that this fruit is an apple, regardless of the presence or absence of the other features. For some types of probability models, naive Bayes classifiers can be trained very efficiently in a supervised learning setting. In many practical applications, parameter estimation for naive Bayes models uses the method of maximum likelihood. In other words, one can work with a naive Bayes model without accepting Bayesian probability or using any Bayesian methods. Despite their naive design and apparently oversimplified assumptions, naive Bayes classifiers have worked quite well in many complex real-world situations. In 2004, an analysis of the Bayesian classification problem showed that there are sound theoretical reasons for the apparently implausible efficacy of naive Bayes classifiers. Still, a comprehensive comparison with other classification algorithms in 2006 showed that Bayes classification is outperformed by other approaches, such as booster trees or random forests. An advantage of naive Bayes is that it only requires a small amount of training data to estimate the parameters necessary for classification. Because independent variables are assumed, only the variances of the variables for each class need to be determined and not the entire covariance matrix. Probabilistic model. Abstractly, the probability model for a classifier is a conditional model. Over a dependent class variable with a small number of outcomes or classes, conditional on several feature variables through. The problem is that if the number of features is large or if a feature can take on a large number of values, then basing such a model on probability tables is infeasible. We therefore reformulate the model to make it more tractable. Using Bayes' theorem, this can be written. In plain English, using Bayesian probability terminology, the above equation can be written as: in practice, there is interest only in the numerator of that fraction, because the denominator does not depend on and the values of the features are given, so that the denominator is effectively constant. The numerator is equivalent to the joint probability model, which can be rewritten as follows, using the chain rule for repeated applications of the definition of conditional probability. Now the naive conditional independence assumptions come into play. Assume that each feature is conditionally independent of every other feature for, given the category. This means that, and so on, for. Thus, the joint model can be expressed as. This means that under the above independence assumptions, the conditional distribution over the class variable is where the evidence is a scaling factor dependent only on, that is, a constant if the values of the feature variables are known. Constructing a classifier from the probability model, the discussion so far has derived the independent feature model, that is, The naive Bayes probability model. The naive Bayes classifier combines this model with a decision rule. One common rule is to pick the hypothesis that is most probable. This is known as the maximum a posteriori or MAP decision rule. The corresponding classifier, a Bayes classifier, is the function defined as follows. Parameter estimation and event models. A class prior may be calculated by assuming equiprobable classes, or by calculating an estimate for the class probability from the training set equals /. To estimate the parameters for a feature's distribution, one must assume a distribution or generate non-parametric models for the features from the training set. The assumptions on distributions of features are called the event model of the naive Bayes classifier. For discrete features like the ones encountered in document classification, multinomial and Bernoulli distributions are popular. These assumptions lead to two distinct models, which are often confused. Gaussian naive Bayes. When dealing with continuous data, a typical assumption is that the continuous values associated with each class are distributed according to a Gaussian distribution. For example, suppose the training data contain a continuous attribute. We first segment the data by the class, and then compute the mean and variance of each class. Let be the mean of the values in associated with class C, and let be the variance of the values in associated with class C. Then, the probability density of some value given a class, can be computed by plugging into the equation for a normal distribution parameterized by and. That is. Another common technique for handling continuous values is to use binning to discretize the feature values, to obtain a new set of Bernoulli distributed features. Some literature in fact suggests that this is necessary to apply naive Bayes, but it is not, and the discretization may throw away discriminative information. Multinomial naive Bayes. With a multinomial event model, samples represent the frequencies with which certain events have been generated by a multinomial, whereas the probability that event occurs. This is the event model typically used for document classification. A feature values are then term frequencies, generated by a multinomial that produces some number of words. The likelihood of observing a feature vector f is given by. The multinomial naive Bayes classifier becomes a linear classifier when expressed in log space. Where and. If a given class and feature value never occur together in the training data, then the frequency-based probability estimate will be 0. This is problematic because it will wipe out all information in the other probabilities when they are multiplied. Therefore, it is often desirable to incorporate a small sample correction, called pseudocount, in all probability estimates such that no probability is ever set to be exactly 0. This way of regularizing naive Bayes is called Laplace smoothing when the pseudocount is 1, and Lodestone smoothing in the general case. Rennie et al. Discuss problems with the multinomial assumption in the context of document classification and possible ways to alleviate those problems, including the use of TF-IDF weights instead of raw term frequencies and document length normalization, to produce a naive Bayes classifier that is competitive with support vector machines. Bernoulli naive Bayes. In the multivariate Bernoulli event model, features are independent Booleans describing inputs. This model is also popular for document classification tasks, where binary term occurrence features are used rather than term frequencies. If is a Boolean expressing the occurrence or absence of the eth term from the vocabulary, then the likelihood of a document given a class C is given by. Where is the probability of class C generating the term? This event model is especially popular for classifying short texts. It has the benefit of explicitly modeling the absence of terms. Note that a naive Bayes classifier with a Bernoulli event model is not the same as a multinomial NB classifier with frequency counts truncated to 1. Discussion. Despite the fact that the far-reaching independence assumptions are often inaccurate, the naive Bayes classifier has several properties that make it surprisingly useful in practice. In particular, the decoupling of the class conditional feature distributions means that each distribution can be independently estimated as a one-dimensional distribution. This helps alleviate problems stemming from the curse of dimensionality, such as the need for datasets that scale exponentially with the number of features. While naive Bayes often fails to produce a good estimate for the correct class probabilities, this may not be a requirement for many applications. For example, the naive Bayes classifier will make the correct MAP decision rule classification so long as the correct class is more probable than any other class. This is true regardless of whether the probability estimate is slightly, or even grossly inaccurate. In this manner, the overall classifier can be robust enough to ignore serious deficiencies in its underlying naive probability model. Other reasons for the observed success of the naive Bayes classifier are discussed in the literature cited below. Relation to logistic regression: in the case of discrete inputs, naive Bayes classifiers form a generative discriminative pair with logistic regression classifiers. Each naive Bayes classifier can be considered a way of fitting a probability model P, X, Y, to optimize the joint likelihood P, X, Y, while logistic regression fits the same probability model to optimize the conditional P, X, Y. The link between the two can be seen by observing that the decision function for naive Bayes can be rewritten as predict 1 if the odds of P, Y equals 1x, are higher than those of P, Y equals 0x. Expressing this in log space gives. The left-hand side of this equation is the log odds, or logit, the quantity predicted by the linear model that underlies logistic regression. Since naive Bayes is also a linear model in the discrete case, it can be reparametrized as a linear function. Obtaining the probabilities is then a matter of applying the logistic function to, or in the multiclass case, the softmax function. Discriminative classifiers have lower asymptotic error than generative ones. However, research by NG and Jordan has shown that in some practical cases naive Bayes can outperform logistic regression because it reaches its asymptotic error faster. Examples: sex classification problem: classify whether a given person is a male or a female based on the measured features. The features include height, weight, and foot size. Training: example training set below. The classifier created from the training set using a Gaussian distribution assumption would be, let's say we have equiprobable classes, so P, male, equals P, female, equals 0.5. This prior probability distribution might be based on our knowledge of frequencies in the larger population, or on frequency in the training set. Testing: below is a sample to be classified as a male or female. We wish to determine which posterior is greater, male or female. For the classification as male, the posterior is given by. For the classification as female, the posterior is given by. The evidence may be calculated. However, given the sample, the evidence is a constant and thus scales both posteriors equally. It therefore does not affect classification and can be ignored. We now determine the probability distribution for the sex of the sample. We're under the parameters of normal distribution which have been previously determined from the training set. Note that a value greater than 1 is okay here. It is a probability density rather than a probability, because height is a continuous variable. Since posterior numerator is greater in the female case, we predict the sample as female. Document classification: here is a worked example of naive Bayesian classification to the document classification problem. Consider the problem of classifying documents by their content, for example into spam and non-spam emails. Imagine that documents are drawn from a number of classes of documents which can be modeled as sets of words where the probability that the ith word of a given document occurs in a document from class C can be written as. For this treatment, we simplify things further by assuming that words are randomly distributed in the document, that is, words are not dependent on the length of the document, position within the document with relation to other words, or other document context. Then the probability that a given document D contains all of the words, given a class C, is. The question that we desire to answer is, what is the probability that a given document D belongs to a given class C? In other words, what is? Now by definition, and Bayes' theorem manipulates these into a statement of probability in terms of likelihood. Assume for the moment that there are only two mutually exclusive classes, S and S, such that every element is in either one or the other. And using the Bayesian result above, we can write dividing one by the other gives, which can be refactored as. Thus, the probability ratio P, SD, /P, SD, can be expressed in terms of a series of likelihood ratios. The actual probability P, SD, can be easily computed from log/P, SD based on the observation that P, SD, plus P, SD, equals 1. Taking the logarithm of all these ratios, we have. This technique of log likelihood ratios is a common technique in statistics. In the case of two mutually exclusive alternatives, the conversion of a log likelihood ratio to a probability takes the form of a sigmoid curve. See Logit for details. Finally, the document can be classified as follows. It is spam if, otherwise it is not spam. See also, AODE, Bayesian spam filtering, Bayesian network, random naive Bayes, linear classifier, logistic regression, perceptron, references. Further reading, Domingos, Pedro. Pazzani, Michael. On the optimality of the simple Bayesian classifier under 0-1 loss. Machine Learning 29, 103 Euro 137 Web, G.I. Boughton, J. Wang, Z. Not so naive Bayes, aggregating one-dependence estimators. Machine Learning 58, 5 Euro 24 doi, 10.1007 per second 10994-005-4258-6 Mosener, M. Deemsar, J. Catton, M. Zupan, Binomograms for Visualization of Naive Bayesian Classifier. Proc. PKDD 2004 PPA 337 Euro 348 Maron, M.E. Automatic Indexing, An Experimental Inquiry. JACM 8, 404 Euro 417 doi, 10.1145/321075.321084 Minsky, M. Steps Toward Artificial Intelligence. Proc. IRE 49 PPA 8 Euro 30 External links, Book Chapter, Naive Bayes Text Classification, Introduction to Information Retrieval, Naive Bayes for Text Classification with Unbalanced Classes, Benchmark Results of Naive Bayes Implementations, Hierarchical Naive Bayes Classifiers for Uncertain Data. Software, Naive Bayes classifiers are available in many general-purpose machine learning and NLP packages, including Apache Mahout, Mallet, NLTK, Orange, Scikit-learn and WEC-R. IMSL numerical libraries collections of math and statistical algorithms available in C++, Fortran, Java and C/NET. Data mining routines in the IMSL libraries include a naive Bayes classifier. Winnow content recommendation open source naive Bayes text classifier works with very small training and unbalanced training sets. High performance, C, any Unix. An interactive Microsoft Excel spreadsheet naive Bayes implementation using VBA with viewable source code. JBNC, Bayesian Network Classifier Toolbox, Statistical Pattern Recognition Toolbox for MATLAB. IFILE, the first really available Bayesian mail spam filter, and classifier. Classifier is a .NET library that supports text classification and text summarization. It is a port of Classifier 4J. Classifier 4J. Classifier 4J is a Java library designed to do text classification. It comes with an implementation of a Bayesian classifier.